Okay, hi everybody. We're going to do section 1.2. Now I realize that some of you have not yet done 1.1, and that's okay. We'll do 1.1 together. 1.2 has a lot of important concepts in it. Most of them aren't very hard, but there's a lot here. So I thought we'd use this opportunity to kind of get some of these definitions taken care of. You will notice that 1.2 has a lot of assigned problems. So I would suggest that as we finish this video, as you're working along, taking good notes for this video, that you then go back and do some of the 1.2 assignment at least, because it is quite a large assignment. 1.2 talks about functions. Now you are all very comfortable and familiar with functions. A function is and I'd love if you were here, you could give me all your different thoughts on it, but a function is a relation in which no first coordinates repeat. So in other words, if you're given a set of ordered pairs, that's what a relation is. It's a set of ordered pairs. You check to see, do any of the x coordinates repeat? Do I have any repeaters? And the answer is no, there are no repeaters, so this one is yes, it is a function. If you had two of the same x values, then it is not a function. And that goes back to something else you learned about functions. They have to pass the vertical line test. So functions, that says functions, must pass the vertical line test. Now, if I just plot these 3 points that I just gave you, just those three, I have 2, 2, 2, 4, and 5, 6. Now, what do you notice about these 2 points right here? The ones that have repeated x values are on top of each other. We don't pass the vertical line test. If they have repeated x values, they're going to be right on top of each other, and they're not going to pass the vertical line test. So, if you have a set of ordered pairs, and it says, is this a function? Just check and see if any of the first coordinates repeat. If you have a picture, check and see if it passes the vertical line test. If you have an equation, you can always whip out your graphing calculator and graph it. That's easy for a lot of people. Somehow you have to visualize or think about, okay, in this equation, could one x give me more than one y? An example might be an equation that looks like this. Because if x is 9, y could be 3, certainly. But if x is 9, y could also be -3, not a function. So if you have an equation and it says, is this equation a function? You're either going to try to graph it on your calculator, you're going to set up some ordered pairs and think about it to make that decision. Now, whenever we talk about functions, we think of the two components differently. So let's back up a minute and consider function notation. Make sure everybody remembers function notation. This says f of x is x squared. F of x is the way we read that. Functions act like input-output machines. So in other words, if you input an x, it's going to square it. So if I input a 2, it's going to give me a 4. If I input a -3, it's going to give me a 9. The x's are the inputs, and the y's are the outputs. If you look at the entire set of inputs, you have what's called the domain. The entire set of outputs is called the range. So domain is associated with inputs, which are the x's. Range is associated with the outputs, which is the y's. Your function values can always be written as ordered pairs. If x is 2, y is 4. If x is -3, y is 9. Always, always, your inputs will be your x's and your corresponding outputs will be your y's. And you can think of those as ordered pairs. For many, many functions, the domain is the set of real numbers. Many functions have a domain of the set of real numbers. For example, if you think about some of the functions we looked at in the P section, we looked at linear functions. This is a linear function. It's a line. It's a line whose y-intercept is -4 and whose slope is 2/1. So up 2/1, up 2/1. Here is the line. Notice that it goes on forever and ever. Its domain is all real numbers. And the set of real numbers is often denoted with this symbol. That's the symbol that means the set of real numbers. If you want to write out real numbers, go ahead. But the domain is all real numbers. That is true for many functions, including this one. The graph of that function is y equals x squared. Looks like this, a parabola, vertex at the origin. That goes on forever and ever and ever, left and right. Remember, domain is x. So when I have a domain question, I'm thinking x. Not up and down, I'm thinking left and right. Domain is left and right. So it goes forever to the left and forever to the right. So that domain would also be the set of real numbers. There are really just 3 times, well, 4 if you count word problems and practical answers. But algebraically, there are 3 times when I really, really, really have to be on the lookout for domain issues, okay? So you need to be ready. Your little domain radar need to go off. Your antenna need to pop up. Your domain antenna. When you have a problem with a variable in the denominator, a problem with a variable under an even root. So when I say even root, I mean square root, 4th root, 6th root, that sort of thing, an even root. Or if your problem involves some kind of a logarithm, any kind of logarithm, okay? So if your problem does not have those 3 things, any of those 3 things, then your domain is going to be all real numbers. So look at this one. There's no fraction, no denominator, there's no radical, and there's no logarithm. So what's the domain? All real numbers. This one, this was the equation y equals x squared. No fraction, no radical, no logarithm, no issue. All real numbers. So let's look at an example of one where we have a problem. Let's say the function is x plus 3 over x minus 4. Now we have a variable in the denominator. And we know that the denominator can never equal 0. So x minus 4 can never equal 0, which means x can never equal 4. So my domain is everything except 4. Now, if you wrote this down as your answer, I would accept it. Now, not everybody's going to, so we're going to talk about the real way of writing it. But I would accept that, because if you say to me x can't be 4, the implication is that x can be anything else. So I'm okay with that. That says, okay, x can be anything I want it to be except -4. Now, the real way of writing that would be -infinity to -4, or -4 to positive infinity. Now, you see what I've done when I write it that way? I've taken every number up to -4, open dot, and then every number after -4, open dot. So what have I included? I've included every single number except -4. I've included all that and all that. You can answer it this way if that's easier. All right, let's look at another one that might give you, that gives us issues. What if we had a problem like this? Now we've got a variable under a radical. We know that whatever is under the radical, must be greater than or equal to 0. It must be positive. So it must be greater than or equal to 0. If it is under a radical and we want to be real, then we need to be positive under the radical. So x minus 2 has to be greater than or equal to 0. Whatever is under the radical must be greater than or equal to 0. So x must be bigger than or equal to 2. Again, I am perfectly fine with that answer. If you want to write it as an integral, that's fine too. It would look like that. You cannot pick an x value. You cannot pick an input value that's less than 2. Because if you pick one less than 2, your output will be imaginary. And you must keep your output real. All right, so let's try one that's got both things going on. How about x plus 5 over x minus 1? How about that? Okay, now we got both issues going on. We have something, we have a variable under a radical, and we have a variable in the denominator. So what do we know about what's under the radical? It must be positive. Kids, this isn't confusing. If it's under a radical, it's greater than 0, period. So x has to be greater than or equal to -5. So far, on my number line, my answer looks like this. Every number greater than or equal to -5. But now I got to deal with this. It's in the denominator. And what do I know about the denominator? It cannot be, whatever is in the denominator cannot be 0. So x cannot be 1. So that means, here's 1, that means I have an opening in my number line at 1, because x can't be that. X can be everything bigger than -5 except 1. Because if it's 1, I have a 0 in the bottom, which is not allowed. So you may write that answer exactly as I said it. X is greater than or equal to -5, but it's not 1. It's okay to write it that way. It's also okay to write it, it's more mathematical to write it, -5 to 1 or 1 to infinity. Take everything from -5 to 1 and then go from 1 on. Now, there are a couple problems I want to look at in your book, so I need you to go to page 102 of your textbook. Page 102 of your textbook, And now we're going to do a little bit of vocabulary work. I hope you wrote these rules down. We're going to spend a lot of time with those rules. They're important. If you didn't write them down, you might want to rewind me and get them written down, because I've erased them. Okay, so we're on page 102 of our book, and we are looking at problem 21. Problem 21 says my function, and they use G, it doesn't make any difference, you know that, you can use whatever name you want, that's just the name of the function. This is the G function. I've been using F function, this is the G function. And it says, tell whether or not it has a point of discontinuity at 0. Now, a point of discontinuity is a break in the problem, and it indicates a domain issue. So what they're really asking you is, do I have a domain issue if I let x be 0? And the answer to the question is, yes, you have a domain issue because x cannot be 0. So it says, do I have a point of discontinuity? Point of discontinuity is a domain issue. Do I have a domain issue? Yes. And then it tells, and then I have to say, so yes. Then it tells me to decide if it's removable or non-removable. This one is non-removable. Now that's not going to make any sense to you until I do the next one. But this problem, which is problem 21, is definitely, I have a point of discontinuity. It's a point of discontinuity is a break in the graph. And breaks in the graph are caused by problems with the domain. One of our domain problems, or one of our red flags that make our antenna go up, is a 0 in the denominator. If you put 0 in here, you are going to have a big problem. Your graph is in trouble. So when it says, do I have a point of discontinuity there? Absolutely I do. Now, it's non-removable, and you'll see what I mean in a minute. Look at problem 22. Problem 22, x cubed plus x over x. I'm using H, I don't know what they use. They use H, yeah. Okay, now, do I have a problem letting x be 0? Absolutely I do. Is there a point of discontinuity? Yes, there is. Because in the problem, written in the textbook, you cannot let x be 0. Because if you let x be 0, you're going to have a 0 in the denominator, and that is an issue. A biggie. It's our Math League t-shirt issue. However, this problem is different because I can't put 0 in. I am not going to put 0 in. It's not allowed. However, I can simplify my problem. If I take an x out of the numerator, notice that that x will cancel and leave me with x squared plus 1. Now the question is still the question. But if I do the simplification, I get a new question. And could I put 0 in this question? The answer is, of course you can. There's no denominator, there's no radical, there's no issue here. You can put 0 in here. Now, you are never going to be able to put 0 in the original problem. So you are going to have a discontinuity. But this one is called a removable discontinuity, because I was able to remove it from the problem. It's still a discontinuity. It's still a break in the graph, but it's a different kind of break. If it's removable, it's going to graph as a whole. In other words, whatever this sketch looks like, I have no idea, whatever it looks like, at the point where x is 0, there's going to be a hole in the graph. You're going to have a curve, and you're going to have a curve, but it's going to skip over that spot. This problem you couldn't remove the discontinuity, so it's going to have a vertical asymptote. That means that when I graph this one, I'm literally going to have an asymptote where x is 0, and I'll have a chunk of the curve over here and a chunk of the curve over here, and they will not be connected. With a removable discontinuity, they're connected. They have a hole, so it skips that point, but where it comes in and where it goes out are the same place. It's connected. This thing is going to be two separate pieces, because that discontinuity was non-removable. Recap. Discontinuities are anything that makes your denominator 0. They're breaks in the curve. There are two kinds. Well, there's more than that, but right now there's two kinds of discontinuities. They're removable and non-removable. To tell if you have a discontinuity, see if anything makes your denominator 0. If anything makes the denominator 0, that's where you have a discontinuity. So in this problem right here, I have a discontinuity at 1. And the discontinuity I have at 1 is non-removable because there's no way to get rid of that. There's no canceling I can do. If you can factor and cancel, like we could in problem 22, it is called a removable discontinuity. It's removable because you could cancel it and remove it from the problem. Vocabulary, important vocabulary. Look at number 25. More vocabulary. State whether each, I'm on 25, page 102, number 25. State whether each labeled point identifies a local minimum, local maximum, or neither. Identify the intervals on which the function is increasing and decreasing. Okay, so there's some function vocabulary in there, talking about max and min, relative or local, max and min. So local and relative are the same thing. So we're talking about local maxes, local or relative mins, same thing. As opposed to absolute maximums and absolute minimums. Now, I am not going to give you definitions for these. You need to know what they mean, period. So when I look at my problem, we've got the point -1, 4. We've got the point 2, 2. And we got the point 5, 5. Okay, so my curve comes in like this and does this. Okay, I didn't draw it as well as they do in the book. I'm going to put arrows on the end because it's going to help my discussion. It's really unclear to me whether they mean there to be arrows or not, so I'm going to put them there so there's no confusion. This point right here is called a local maximum. It's the top of a hill. This point is called a local maximum. It's the top of a hill. Tops of hills are local maximums. So in a sine wave, which goes on forever and ever like this, there will be infinitely many local maximums. These are your local maximums. So there are two local or relative maximums, -1, 4 and 5, 5. This guy is called a local or relative minimum. The bottom of a valley is a local minimum. So again, the sine wave would have many of those. You can have infinitely many relative maximums and relative minimums, just depending on the shape of your curve. This one has two hills and a valley, so it has two maxes, relative maxes, local maxes, and one local min. The absolute maximum is the very highest point on the curve. So for us, this would be the absolute maximum. It is the very highest point on the curve. The absolute, and there is one. There's only going to be one absolute maximum. There's only one very highest point on the curve. Now, you're looking down here and you're saying, well, Mrs. Ford, and you're right. The sine curve is an anomaly. It's a cool curve, but all of these would also be absolute maxes, and there are a ton of them. Generally speaking, you have one highest point. Lowest point. Well, take a look at that curve. I put those arrows on there for a reason. I don't want any confusion. That curve goes on forever and ever down. So there is no absolute minimum. This thing goes down forever and ever and ever. So when you tell me a curve has no absolute minimum, that tells me that it goes to negative infinity. This is my absolute max, and I don't have an absolute minimum. I don't have a lowest point. Could you put negative infinity? I suppose you could. That's not really a point, but it does indicate that it goes on forever and ever. Now, when we consider increasing and decreasing, I'm reading the question, it talks about increasing and decreasing. When I consider increasing and decreasing intervals, I always work left to right. Now that should be easy for you. Everything you do is left to right. You read left to right, right? You write left to right. So when I'm reading a graph, I read it left to right. So I'm going to start my pencil right here, and notice it's going to go up. And it's going to go up until it gets to here, and then it's going to go down, and then it's going to go up again, and then it's going to go down. When my pencil is going up, I have an increasing interval. When my pencil is going down, I have a decreasing interval. Okay, so where am I increasing? Well, I am increasing from the beginning of the curve, which would be negative infinity. I'm looking at the x values now. My intervals are x values. So I'm increasing from negative infinity to negative 1. Now, please never include, when you're doing an interval, an increasing or decreasing interval, never include the endpoint. Because at this point, if you're on this dot, you aren't increasing or decreasing. So everything up to negative 1 is increasing. And then again, everything from 2 to 5 is increasing. And I am looking at x values, not y values. They happen to match. But I am looking at x values when I write an interval of increasing or decreasing. Now, where am I decreasing? Well, I'm decreasing from negative 1 to 2. And then I am decreasing again from negative 1 to 2, and then again from 5 to negative infinity. Pencil going up, increasing. Pencil going down, decreasing. It's that simple. Those are intervals, so we will write them in interval notation. Now, another bit of vocabulary. I'm going to draw 3 shapes up here, and we're going to talk about them. Okay. Now we're going to talk about boundedness. And basically, what boundedness means is you have a ceiling and a floor. If you are bounded, you have a ceiling and a floor. If all you have is a ceiling, then you're called bounded above. If all you have is a floor, it's called bounded below. To be bounded, you have to have a ceiling and a floor. I didn't erase my sine curve. Here it is, some of it anyways left. Does the sine curve have a floor? Yes, it never goes lower than this. This is its floor. Does it have a ceiling? Yes, it never goes above this point. That's its ceiling. So this curve would be bounded because it has both a floor and a ceiling. All right, let's look at this parabola. This parabola is not bounded because it does not have a ceiling. However, it does have a floor. It has a point beyond which it does not go. It is said to be bounded below at -2. So it is 2 down. So its floor, if you imagine a floor down here, its floor is at -2. So it is called bounded below. All right, now let's look at this one. This thing right here. This is not a bounded function. It passes the vertical line test, it's a function. But it is not bounded because to be bounded, you must have a floor and a ceiling. And all this guy has is a ceiling. So this one is said to be bounded above at 2. 2 is a ceiling. That's an asymptote that the curve is going to approach as it heads off the page. Now look at this guy. This guy is bounded. Why is he bounded? Because he is bounded below at 0 and above at 4. When you are bounded above and below, you are called bounded. I did not bring a calculator with me, honestly. Had to come upstairs to get some light, and I forgot to bring a calculator with me, but I don't think I need one. There are some questions in section 1.2 that ask you to graphically find the maximum and the minimum. So you're going to graph the equation, whatever the equation happens to be. You're going to graph it. And this time when you graph it, it is critical that your window is set big enough to allow you to see the top of the hill and the bottom of the valley. Now, up to this point, we've been looking for the x-intercepts. So we haven't really cared if we saw all this or we saw all that. Now we have to. Because if we're looking for a maximum, we need to be able to see it on our calculator. To find that point, once you have your curve sketched, to find that point, you do exactly what we did to find the zeros. So you're going to press second calc. Only this time in your list of options, you're going to choose, if you're looking for that point, you're going to choose max. And as soon as you press max, it's going to say left bound. So set your cursor over here somewhere on the left side of the max. You'll set it, and it'll put that little arrow up there. Then it'll say right bound, so move it over here so it's on this side of the hill. And then it'll say guess, move it up here so it's on that point, and it will give you the maximum point. Okay, so again, I don't need to go through this with you because it is exactly like what you do when you find the x-intercepts, except when you go into second calc, instead of choosing 0, you're going to choose max or min. And you have to do them separately, obviously one at a time. Second calc, min. Set your left bound over here, set your right bound over here, take your guess, and you got it. So those are easy. I don't anticipate you're going to have any trouble with those. One more huge idea that we need to talk about in terms of functions, and that is symmetry. Now, if I were to draw, I said symmetry, in case you missed that word. If I were to draw this parabola, everybody in the room, there's Mr. Fogel interrupting the video.
Want to do a math kit.
Everybody would look at this picture and say, that is indeed symmetric. It is symmetric about this line right here, which is the y-axis. So we would say this thing is symmetric about the y-axis. It has what we call y-axis symmetry. Curves that have y-axis symmetry are called even functions. That's important. If you want to know if a function is even, what you have to decide is it symmetric about the y-axis? The word even is not coincidental. This function is y equals x squared. And we're going to talk more about that in a minute. There are lots of even functions, though. They don't have to have x squareds. So I probably shouldn't have even said that, but that's where the word came from. Now let's look at this function. Now what symmetry means is, boys and girls, if you're symmetric about the y-axis, it means you fold your paper on the y-axis and it doubles right back over onto itself. So if I folded my paper on the y-axis, these two would come together. They would be right on top of each other. That's what it means to be symmetric. If I fold this across the y-axis, if I folded this, that would end up over here and that would end up over here. It would not go on top of each other. This has no y-axis symmetry. This is not an even function. It does not have y-axis symmetry. What symmetry does it have? Think about how you could fold that paper so that the two pieces would double over onto themselves. Actually, there are several folds you could make. Two of them are extremely important. One would be this fold right here. If you folded your paper on that line, wouldn't these pieces come back on top of each other? Absolutely. This has symmetry about the identity line. And the identity line is the line y equals x. Think about, this isn't really a line, but think about if you took your picture, this picture, and you flipped it this way, you folded it this way, diagonally. It has symmetry about the origin. What that means is, if this is the point 1, 1, and I'm making that up, but let's just say that's the point 1, 1, then this would be the point -1, -1. It's exactly the same point in the opposite quadrant. If a function has symmetry about the origin, this particular function happens to have different kinds of symmetry, and that's okay. That's absolutely fine. But if a function has symmetry about the origin, it is called an odd function. This function is an odd function. If you took this and flipped it across the origin, now I'm not folding it across the x-axis, I am flipping it across the origin, it would double back on itself. This is the function x cubed. It has symmetry about the origin. It is an odd function. But there are many other odd functions. They don't have to have an odd exponent. There are many other odd functions. This is an example of one. Okay. All right, now this is kind of a big concept. I really need you to get it. So we're going to talk about symmetries. You ought to be able to look at a picture and tell me if it's symmetric about the y-axis, or we didn't talk about this one, but certainly we could be symmetric about the x-axis. No special name for that. Y-axis is even. You can tell me if you have symmetry about the identity line, that's this line right here, or if you have symmetry about the origin. And if you have that symmetry, you are odd. This one doesn't have a special name. Actually, I gotta be careful. It sort of does, but we're not gonna talk about it yet. The two special names you need to know are even and odd. Even is symmetry about the y-axis. Odd is symmetry about the origin. Now, the issue is going to come when I give you an equation and ask you about its symmetry. All right, so we need to talk about the tests of symmetry. And these will make sense. I know what you're going to do. You're going to memorize this stuff, and that's okay. But it really, really, really should make sense. It has to do with input and output. So let's say that our function is f of x equals x squared minus 3. Okay, that's our function. I am going to test it for symmetry about the x-axis, the y-axis, the origin, and the identity line. Those are the 4 symmetries I am going to be interested in. And we had examples of all those up here earlier. Okay? Now, first thing I'm going to do is rewrite my equation as y equals x squared minus 3. If you are symmetric about the x-axis, think about this, we're symmetric about the x-axis. That means if this is the point 2, 3, what is this point if these are symmetric? That would be the point 2, negative 3. Would you agree with that? So here's what I want you to do. I want you to come over here, and I want you to, in this equation right here, I want you to change the sign on the y coordinate. So change the sign of y. Okay? Now, all right, so that gives me negative y equals x squared minus 3, which means y equals negative x squared plus 3. If I have symmetry, then a change in the y coordinate has no impact on the x coordinate. In other words, I should have exactly the same equation if I change the sign on y. Now, when I change the sign on my y coordinate, did I end up with the same equation? No, I did not. So this one has no symmetry about the x-axis. This picture, when you graph that. Again, the test is change the sign of y. If you have symmetry, you will get exactly the same equation that you started with. Well, I didn't, so I don't have symmetry. All right, let's do the y-axis. Change the sign on x. If you have symmetry about the y-axis, kids, This will be the point 1, comma 2. This will be the point negative 1, comma 2. So I should have no impact on y if I change the sign on x. Well, let's see. Go back to the original problem. That would be y equals negative x squared minus 3. Simplify it. Y equals x squared minus 3 because the negative squares out. Well, looky there. That's exactly what I started with. I changed the sign of x, but I got exactly the same equation. So what does that mean? That means this one has y-axis symmetry, which means, by the way, since it has y-axis symmetry, it is an even function. Now, think about what happens if you have symmetry to the origin. We kind of talked about it. You go from this quadrant to this quadrant. What happens to your signs? They both change. They both change. So we're going to change both signs. I'll have to do that one somewhere else. I'm running out of room. So we're going to change both signs. So our equation would be negative y equals negative x squared minus 3. So negative y equals x squared minus 3, and y equals negative x squared plus 3. Now, does that equation right there match the original one I started with? No. So we have no symmetry about the origin, which, oh, by the way, if we're not symmetric about the origin, we are not odd, right? Because the only way you can be odd is if you have symmetry about the origin. Now I'm going to do the line y equals x. The test is, I'll write that down here, the test is switch the variables. So for y equals x, I would have x equals y squared minus 3. That's not even close to being the same equation, so that's a no. Now, the example I did earlier, I had something up here that had 2 symmetries, remember? So I don't want you to think that you're only going to get one of these that's a yes. You may get more than one that's a yes. You may get none that are yeses. There are curves that aren't symmetric to anything. But these are the tests. Now, this last one in particular, kids sometimes think, gosh, are there functions that you can switch the variables and it's the same equation? Well, think about this equation for a minute. Think about that equation. If I switch the, so here's my original. If I switch the variables, I get this. Now, at first glance, that looks different. But if you multiply the y over here, and then divide by x, what happens? You get the same equation. So that one, this one does have symmetry about the identity line. If you switch the variables and do a little, maneuvering, they match. So that one does. All right, we're going to do one more example. So you've got these written down because I'm out of room. Okay, it's written down. Here we go. The question is this. By the way, you need to know these. So if I went too fast and now I'm erasing or you didn't write them down, you need to rewind me and get them written down. Question might be, is this function even, odd, or neither? Now, even, odd, or neither. If you're testing for evenness, this isn't asking me for all the symmetries. It's asking me for even or odd. So if I'm even, that's y-axis symmetry. If I'm odd, that's origin symmetry. So if the question is, are you even or odd, you're only going to do 2 symmetries. Of the 4 tests that I gave you, I'm going to do 2. So let's do y-axis first. What's the test for the y-axis? In your equation, oh, well, first of all, let's think of this as y equals 2x cubed plus x. All right, in my equation, I'm going to change the sign of all of the x's. So I'll have y equals 2 negative x cubed plus negative x. Every time I see an x in my equation, I'm going to replace it with a negative x if I'm doing y-axis symmetry. All right, so then I simplify. So I have negative 2x cubed, because a negative cubed is still negative, minus x. Does this equation match the original? No. Therefore, it is not even. All right, so now I'm going to check for odd. Odd means symmetric about the origin. What's the test for the origin? You change both signs. So go back to the original equation. Negative y equals 2 times negative x cubed plus negative x. I'm changing both signs. Then I simplify. So negative y equals negative 2x cubed minus x. Dividing by the negative gives me 2x cubed plus x. Does that match the original problem? Yes. Which means this does have symmetry about the origin, so it is indeed an odd function. Do you think there are things that are neither? Oh yeah, millions of them. But if the question is, are you even or odd, you need to do your test of symmetry for the y-axis and for the origin. Okay? All right, there's a lot in this. We're almost done, kids. I promise. We have one more thing to talk about. The last thing we have to talk about are asymptotes. We've kind of already talked about vertical asymptotes. Do you remember where my vertical asymptote came from? My vertical asymptote came from having a 0 in the denominator that I couldn't remove. It was a non-removable discontinuity. Vertical asymptotes happen when you have a 0 in the denominator. Okay, and you can't get rid of it. It's a non-removable, so I'll put that word here, non-removable. Okay? Now, let's look at a couple of examples. F of x equals 3x plus 1 over x minus 2. I'm not asking you to sketch this just yet. We're going to sketch them, but not just yet. Right now, where is the vertical asymptote? What makes the denominator 0? 2. So you're going to have a vertical asymptote where x equals 2. How do I know it's non-removable? I can cancel anything. There's no factoring to do. The only way you can remove it is to cancel it. Obviously, I can't cancel. It's a non-removable discontinuity, a vertical asymptote at 2. All right, let's look at another one. Big problem. We're going to learn how to graph this by ourselves with no calculator. We're going to be able to do that, but not right now. Right now we're talking about asymptotes. All right, vertical asymptotes. Nothing in that problem cancels. So we're going to have two vertical asymptotes. We're going to have one at 2 and one at -3. Got it? Vertical asymptotes, easy. What makes the denominator 0? If you can't cancel it out, it's a vertical asymptote. Now, horizontal asymptotes are a little bit trickier. It's easy, but it's kind of hard to explain. A horizontal asymptote is a limit. Now, that word doesn't mean anything to you right now. It will, if I do my job. But right now, just kind of go with me here for a second. When I look at this fraction right here, I'm going to put a horizontal asymptote in this problem. When I look at this fraction, think about letting x get really big. So think about building a T-chart and think about putting in really big values of x. Now, I'm not talking about like 20. I'm talking about like 20 trillion. Really big numbers. When you put in really big numbers, how significant is a 1? This is what I mean. If you put 1 million in here, you have 3 million plus 1. How significant is that 1? It isn't. If you put 1 million in here, how significant is that 2? It isn't. Right? 1 million minus 2 is still just about 1 million. So basically, if x is a giant number, these two things really don't mean anything. And what you have is essentially like 3 million over 1 million. Not exactly, because you're still adding and subtracting a little teensy bit. But it's pretty close to 3 million over 1 million. Which reduces to what? 3. Your horizontal asymptote is at 3. So if I had 5x plus 1 over 7x minus 2, my vertical asymptote would be x equals 2/7, because 2/7 would make that 0, and vertical asymptotes happen when your denominator is 0. My horizontal asymptote would be y equals 5/7, because if x is 1 million, the numerator is about 5 million, and the denominator is about 7 million, and 5 million over 7 million is 5/7. All right, what about this one? Well, you got to really think about this for a second. When I FOIL out the top, I'd have a 12x squared. Now, I know plus some other stuff. I get that. But I'd have 12x squared, right? And on the bottom, I would have an x squared plus some other stuff. Now, I am doing a horizontal asymptote. So I am not paying attention to the other stuff. None of that matters. Because if I'm talking about numbers like 1 million, 1 billion, 1 trillion, 1 million squared is the dominant force in this problem. Now, will there be some x's? Yeah, and there'll be millions, there'll be big numbers, but not compared to 1 million squared. When I'm doing horizontal asymptotes, kids, I am focusing on the biggest power I have. Because as I let x get humongous, unbelievably big, you can't even imagine how big it is. As I let x get that big, the biggest power is where the power is. I mean, that's where the action is. So I've got 12x squared over x squared, so my horizontal asymptote is at y equals 12. All right, we'll do one more of those, and then we'll be done. Actually, we might do 2 more, and then we'll be done. Actually, maybe we'll do 3 more. now that I think about it. I want to talk just about horizontal asymptotes. Vertical asymptotes I think we've got, but I want to find the horizontal asymptote. All right, of these functions. Let's say 3x minus 8 over 5x plus 2. Let's say 3x squared minus 8 over 5x plus 2. And let's say 3x minus 8 over 5x squared plus 2. All right, we got some different things happening here. The first one is the easy one. This is the kind we've been talking about. Your horizontal asymptote will be y equals 3/5. Because you have an x over an x, nothing else matters. 3/5 is your horizontal asymptote. This one is a little bit different, because you notice that you have a bigger power on the top than you do on the bottom. And if you were listening to me a minute ago, I said when I do horizontal asymptotes, what do I key in on? The highest power in the problem. So in this case it was x. So I keyed in on 3x over 5x. The biggest power in this problem is x squared. I do not have an x squared in the denominator. So when I compare my highest power, which is x squared, instead of getting a nice little fraction like 3/5, I get a fraction like 3 over 0. No horizontal asymptote. You can't have 3 over 0. If a horizontal asymptote, kids, can act like a ceiling. If you don't if your biggest power is on top, then that fraction is just going to keep growing and growing and growing. It's going to shoot up into space. It isn't going to have an asymptote. It's not going to approach anything. It's going to head off into space. 3 over 0, no horizontal asymptote. The memorizers among you are going to memorize that if the power on top is bigger, there is not a horizontal asymptote, ever. Now, what about the other way around? I am still looking at the highest power in the problem. It is still x squared. But this time, I have no x squareds on the top. I have to compare power, x squared to x squared, or x to x, or x cubed to x cubed. I can't mix and match. So if I don't have it, I'm going to put it in there as a 0. So 0x squared over 5x squared. Instead of getting a nice neat fraction like 3/5, instead of getting this really bad situation, 3 over 0, I got the situation 0 over 5. Well, what is 0 over 5? 0. This horizontal asymptote is at y equals 0. If the power on the bottom is bigger, the fraction is going to continue to get smaller and smaller, because the denominator will grow as x changes. As x gets bigger, the denominator will grow faster than the numerator. Therefore, the fraction will approach 0. The memorizers among you are going to memorize that if the power on the bottom is bigger, the horizontal asymptote will always be at 0. If the power on the bottom is bigger, it's going to be at 0. If the power on top is bigger, there isn't going to be one. And ideally, the powers will match, so your answer will just be the fraction of their coefficients. That's how we get horizontal asymptotes. Quick recap, we get vertical asymptotes by checking to see what makes the denominator 0. So for this problem, my vertical asymptote would be x equals negative 2/5. Negative 2/5 is the number that makes that 0. If I try to make that 0, I get negative 2/5. That's where my vertical asymptote is. That's it. So everybody is responsible now. You should be able to work on all of the homework problems in section 1.2, and you're responsible for all of the vocabulary that we discussed today. The first time, if you are not alpha period, the first time I see you will be your test day. So you will take your test. I don't know if I see you on Monday. I don't know if I see you on Tuesday. But the first time I see you will be your test. And we will cover then 1-1, 1-3, 1-4. We'll do all those together in class. But this is 1-2. Make sure you have taken good notes. Go back and replay if you need to. Lots of information here that's important. All right, have a great weekend. I'll see you.